Right now, as you watch this video, something impossible is happening. Your brain is constructing a three-dimensional world from flat signals on your retina. Light hits a two-dimensional surface at the back of your eye, and somehow, impossibly, you experience depth, volume, space. You reach out and touch objects that feel solid, real, undeniably three-dimensional. But here's what will keep you awake tonight. The greatest minds in theoretical physics have discovered that this might not be a quirk of human perception. This might be the fundamental nature of reality itself. Everything you see, everything you touch, every atom in your body, every star in the sky, all of it might be a projection from a two-dimensional surface at the edge of the universe. You are not living in three dimensions, you are a hologram. This sounds like science fiction. It sounds like the kind of wild speculation that belongs in late-night conversations, not in the equations of Nobel Prize-winning physicists. But in 1973, a physicist named Jacob Bekenstein made a discovery about black holes that would eventually unravel our understanding of space itself. He was working at Princeton University, trying to solve a problem that had been bothering physicists for years. Black holes seem to violate the second law of thermodynamics, one of the most sacred principles in all of physics. When matter falls into a black hole, it disappears from our universe. Its entropy, its disorder, seems to vanish. But the second law says entropy can never decrease in a closed system. The universe's disorder must always increase or stay the same, never decrease. Bekenstein proposed something radical. What if black holes have entropy? What if they contain disorder, information, hidden from our view? But here's where it gets strange. When he calculated how much entropy a black hole should have, he discovered something that made no sense. The entropy wasn't proportional to the volume of the black hole. It was proportional to its surface area. Imagine you have a box. Common sense tells you that the amount of information you can store in that box depends on its volume, how much space is inside. The bigger the box, the more information. But Bekenstein's equations said something different. For black holes, the information isn't stored in the volume. It's stored on the surface, on the event horizon, the two-dimensional boundary. 1 year later, Stephen Hawking refined these calculations at Cambridge University. He proved that black holes emit radiation, and he confirmed Bekenstein's bizarre result. The entropy of a black hole, the maximum amount of information it can contain, is determined entirely by the area of its event horizon, not its volume. This is called the Bekenstein-Hawking entropy, and it's measured in units of Planck areas. Each Planck area on the event horizon can store exactly one bit of information, one quantum of yes or no, 1 or 0, on or off. Think about what this means. A black hole the size of our solar system doesn't store information throughout its vast interior volume. All the information about everything that ever fell into it, every star, every planet, every particle, is encoded on its two-dimensional surface. Like a hologram. You've seen holograms before, those shimmering images on credit cards, those three-dimensional displays at museums. They work by encoding three-dimensional information onto a two-dimensional surface using interference patterns of light. When you look at a hologram from different angles, you see different perspectives of a three-dimensional object. But the object isn't really there. It's a projection. All the information needed to create that three-dimensional image is stored in the two-dimensional holographic plate. Now imagine something incredible. What if our entire universe works the same way? In 1993, a Dutch physicist named Gerard 't Hooft was working at Utrecht University, thinking about these strange properties of black holes. He had won the Nobel Prize for his work on the fundamental forces of nature, and he was deeply troubled by what black holes implied about information. He proposed something that seemed insane. Maybe the three-dimensional universe we experience is actually a hologram. Maybe all the information in any volume of space is actually encoded on the boundary of that volume, on its surface. He called this the holographic principle. 2 years later, Leonard Susskind at Stanford University developed this idea further. Susskind had been fighting with Stephen Hawking for years about what happens to information when it falls into a black hole. Hawking said information is destroyed. Susskind said it must be preserved. The holographic principle offered a solution. Information isn't destroyed when it falls into a black hole. It's encoded on the event horizon. The three-dimensional interior is a projection of the two-dimensional surface. And if this is true for black holes, Susskind argued, it might be true for the entire universe. Let me make this concrete. Take any region of space, any volume, a room, a planet, a galaxy. According to the holographic principle, the maximum amount of information that can exist in that volume is not determined by how many Planck volumes fit inside it. It's determined by how many Planck areas fit on its boundary, on its surface. The three-dimensional space inside is somehow encoded on the two-dimensional surface surrounding it. This is not a metaphor. This is not a philosophical idea. This is a mathematical principle that emerges from our best theories of quantum gravity. And it gets stranger. In 1997, a physicist named Juan Maldacena made a breakthrough that would change everything. He was working at Harvard University, trying to understand string theory, the idea that fundamental particles are actually tiny vibrating strings. Maldacena discovered something called the ADS-CFT correspondence. The name doesn't matter. What matters is what it proved. He showed mathematically that a particular type of universe with gravity in 3 dimensions is exactly equivalent to a theory without gravity in 2 dimensions. Not similar, not analogous, exactly equivalent. Every event in the 3-dimensional universe with gravity corresponds to an event in the 2-dimensional universe without gravity. They are 2 descriptions of the same reality. Imagine you're watching a movie. The movie shows a 3-dimensional world with people, buildings, landscapes. But the movie itself is stored on a 2-dimensional disc. The DVD contains all the information needed to reconstruct the 3-dimensional scenes. Now imagine that the 3-dimensional world in the movie is just as real as the 2-dimensional information on the disc. Neither is more fundamental than the other. They're 2 ways of describing the same thing. That's what Maldacena proved, mathematically, for certain types of universes. His paper became the most cited paper in theoretical physics. Thousands of physicists have spent decades exploring its implications. And here's what they've found. The holographic principle isn't just true for black holes or for abstract mathematical universes. It might be true for our universe. Think about the universe you live in. You experience 3 dimensions of space: left, right, forward, backward, up, down. You can move in any of these directions. Space feels 3-dimensional. But according to the holographic principle, all the information about everything in the universe, every particle, every force, every event, might be encoded on a 2-dimensional surface. Where is this surface? At the edge of the universe, at the cosmic horizon. The universe has a horizon, just like a black hole. It's the boundary beyond which light hasn't had time to reach us since the Big Bang. This cosmic horizon is approximately 46 billion light-years away in every direction. That's the edge of the observable universe. And according to the holographic principle, that distant 2-dimensional surface might contain all the information about everything inside, including you. You are not a 3-dimensional being living in 3-dimensional space. You are information encoded on a 2-dimensional surface at the edge of the universe, experiencing yourself as a 3-dimensional projection. Let me give you a sense of scale. The cosmic horizon has a surface area of approximately 10 to the power of 123 square meters. That's a 1 followed by 123 zeros. Each square Planck length on that surface, the smallest possible unit of area, can store 1 bit of information. That means the maximum amount of information in the entire observable universe is about 10 to the power of 123 bits. This is called the Bekenstein bound. It's the ultimate limit on information in our universe. And it's determined not by the volume of the universe, but by the area of its boundary. Now here's where your brain starts to hurt. If the universe is a hologram, Where is the underscore, quote, underscore, zero underscore reality? Is it the three-dimensional space you experience, or is it the two-dimensional surface at the cosmic horizon? The mathematics says they're equivalent. Neither is more real than the other. They're two descriptions of the same thing. But our brains evolved to experience the three-dimensional description. We feel like we're moving through three-dimensional space because that's the useful way for our brains to process the information. But the information itself might be stored elsewhere, on the boundary. Think about a video game. When you play a video game, you experience a three-dimensional world. You walk through buildings, you see landscapes stretching into the distance. But that three-dimensional world doesn't exist anywhere except as information in the computer's memory. The computer stores numbers, coordinates, colors, textures, and constructs a three-dimensional experience for you. The three-dimensional world is a useful interface, but it's not where the information actually lives. The information lives in the computer's circuits. In our universe, the underscore, quote, underscore, one underscore might be the two-dimensional surface at the cosmic horizon. In 2010, a Japanese physicist named Yoshifumi Hyakutake provided new evidence for the holographic principle. Working at Ibaraki University, he and his team performed incredibly complex calculations. They calculated the internal energy of a black hole in a three-dimensional universe. Then, they calculated the internal energy of the corresponding two-dimensional universe without gravity. The numbers matched perfectly, within the margin of numerical error. This was stunning confirmation that Maldaceno's correspondence wasn't just mathematical abstraction. It was describing something real about how universes work. But if we're holograms, why don't we notice? Why does space feel three-dimensional? The answer lies in the nature of information and projection. When you look at a hologram, you don't see the interference patterns on the holographic plate. You see the three-dimensional image. The projection is what's accessible to you. Similarly, we don't experience the two-dimensional information at the cosmic horizon. We experience the three-dimensional projection. Our brains, our bodies, our entire existence is part of that projection. We're inside the hologram, so we experience it as three-dimensional reality. Here's another way to think about it. Imagine you're a character in a video game. You experience the game world as three-dimensional. You can't see the code running in the computer's processor. You can't access the underlying information. You only experience the projection, the rendered three-dimensional world. If you tried to investigate the fundamental nature of your reality, you discover that everything you can measure, everything you can interact with, is consistent with being in a three-dimensional world. But a programmer looking at the code would see something different. They'd see information stored in computer memory being processed and projected as a three-dimensional experience. We might be in a similar situation. When we do experiments, when we measure particles and forces, we're measuring the projection, the three-dimensional description. And that description is perfectly consistent and self-contained. We can do physics, we can make predictions, we can build technology, all within the three-dimensional description. But the underlying information, the underscore, quote, underscore, two underscore, might be stored on a two-dimensional surface we can never directly access. In 2015, physicists at the University of Vienna performed an experiment that brought the holographic principle into the laboratory. They created a quantum system that exhibited holographic properties. Using ultra-cold atoms trapped in laser beams, they showed that the entropy of the system scaled with its boundary area, not its volume. This was the first experimental evidence that holographic behavior isn't just a property of black holes or abstract mathematical universes. It can happen in real physical systems we can build and measure. The implications are staggering. If the universe is a hologram, then space itself is not fundamental. Space is emergent. It's a useful way of organizing information, but it's not the deepest level of reality. The deepest level might be the information encoded on the cosmic horizon. Space, time, even gravity might be emergent phenomena, patterns that arise from the way information is organized and processed on that distant two-dimensional surface. Think about temperature. Temperature feels real. You can measure it, you can feel it, but temperature isn't fundamental. It's an emergent property of molecular motion. When molecules move faster, we experience higher temperature. Temperature is a useful concept, but it emerges from something more fundamental. Similarly, space might be an emergent property of information. The three dimensions you experience might emerge from the way information is organized on a two-dimensional surface. This raises a profound question. If space is emergent, what about time? Some physicists believe time might also be emergent, that at the deepest level of reality, there is no time. There is only information, organized in patterns. The flow of time we experience, the sense that the past is fixed and the future is open, might be an illusion created by the way information is processed in the holographic projection. In 2017, a team of physicists led by Ning Bao at the University of California, Berkeley, developed new mathematical tools to study the holographic principle. They showed that the principle places fundamental limits on how much information can be stored in any region of space, and how quickly that information can be processed. These limits are far beyond anything we can currently measure, but they're there. The universe has a maximum information density, and it's determined by the holographic principle. Here's what that means for you, personally. Your body contains approximately 7 octillion atoms. That's 7 followed by 27 zeros. Each atom contains information, the positions and momenta of its electrons, the quantum states of its nucleus. Your brain contains approximately 86 billion neurons, each connected to thousands of others, creating trillions of synapses. The information content of your brain is staggering. But all of that information, every thought you've ever had, every memory, every sensation, is encoded somewhere on the two-dimensional surface at the edge of the universe. You are not here, not in the way you think. The quote, "3 you experience" is a projection. The real information that constitutes you is spread across a distant two-dimensional surface, 46 billion light-years away in all directions. And yet, you experience yourself as a localized, three-dimensional being, sitting in a chair, watching a screen. The projection is so perfect, so seamless, that you never notice the underlying reality. But now you know. And once you know, you can't unknow it. Every time you reach out and touch something solid, you'll remember that solidity is a projection. Every time you look at the stars, you'll remember those stars are information encoded on a distant surface. Every time you think a thought, you'll remember that thought is a pattern in a holographic projection. The holographic principle changes everything. It changes what we mean by quote 4. It changes what we mean by quote 5 and quote 6. It changes the fundamental nature of space itself. And it raises questions that physicists are still struggling to answer. If space is emergent, if the 3 dimensions you experience are projections from a two-dimensional surface, then something else must be fundamental. Something must connect the information on that distant boundary to create the illusion of locality, the feeling that you are here and not there. In 2009, a physicist named Mark van Ramsdonk at the University of British Columbia discovered what that something might be. He was studying the mathematics of the holographic principle, working through the equations of the ADS-CFT correspondence, when he noticed something extraordinary. The thing that holds space together, the thing that makes distant points in space feel separate and distinct, is quantum entanglement. Quantum entanglement is one of the strangest phenomena in physics. When 2 particles become entangled, they form a connection that transcends space. Measure the spin of one particle, and you instantly know the spin of the other, no matter how far apart they are. Einstein called this quote 7, and he hated it. He thought it proved quantum mechanics was incomplete. But experiment after experiment has confirmed that entanglement is real. It's not a flaw in quantum mechanics, it's a fundamental feature of reality. Van Ramsdonk discovered that in the holographic universe, entanglement isn't just a weird quantum phenomenon. It's the glue that holds space together. Imagine the two-dimensional surface at the cosmic horizon. It contains all the information about our universe, encoded in quantum bits. Now imagine that these bits are entangled with each other in complex patterns. Van Ramsdonk showed mathematically that the amount of entanglement between different regions of the boundary determines the geometry of the three-dimensional space that emerges. More entanglement means the corresponding points in three-dimensional space are closer together. Less entanglement means they're farther apart. Space itself, the distance between objects, emerges from the pattern of quantum entanglement on the boundary. This is not a metaphor. This is what the mathematics says. When you walk across a room, you're not moving through pre-existing space. You're experiencing a change in the entanglement pattern of quantum information on a distant two-dimensional surface. The room feels three-dimensional because the information on the boundary is highly entangled in a particular pattern. That pattern creates the projection you experience as three-dimensional space. Think about what this means for the nature of distance. Right now, your hand is approximately half a meter from your face. That distance feels real, physical, absolute. But according to Van Ramsdonk's discovery, that distance is actually a measure of how entangled the quantum information representing your hand is with the quantum information representing your face on the two-dimensional boundary. The half-meter distance you experience is an emergent property of entanglement patterns. In 2013, physicists Leonard Susskind and Juan Maldacena took this idea even further. They were trying to understand what happens when you create a wormhole, a tunnel through space-time that connects two distant points. Wormholes are solutions to Einstein's equations of general relativity, but nobody knows if they actually exist in nature. Susskind and Maldacena discovered something remarkable. A wormhole connecting two black holes is mathematically equivalent to quantum entanglement between those black holes. They called this ER equals EPR, a technical way of saying that Einstein-Rosen bridges, which are wormholes, are the same thing as Einstein-Podolsky-Rosen entanglement, which is quantum entanglement. This means that when two particles are entangled, they're connected by a tiny wormhole. The wormhole is far too small to send information through, far too small to travel through, but it's there. It's the geometric manifestation of entanglement. And if space is made of entanglement, then space is made of wormholes. Countless tiny wormholes connecting every point to every other point, creating the fabric we experience as three-dimensional space. Your brain contains approximately 86 billion neurons. Each neuron is connected to thousands of others through synapses. The pattern of connections creates your thoughts, your memories, your consciousness. Now imagine something similar happening on the cosmic horizon. Quantum bits of information, entangled in incomprehensibly complex patterns, creating connections that manifest as the three-dimensional universe. Your neurons are connected by electrochemical signals traveling through physical space. The quantum bits on the boundary are connected by entanglement, and that entanglement creates physical space. But here's where it gets truly strange. If space emerges from entanglement, then space can disappear if entanglement is destroyed. Van Ramsdonk showed this mathematically. If you gradually reduce the entanglement between different regions of the boundary, the corresponding three-dimensional space begins to tear apart. Reduce the entanglement enough, and space ceases to exist. The universe fragments into disconnected pieces. Space is not a stage on which events happen. Space is a phenomenon that exists only when quantum information is entangled in the right way. In 2016, a team of physicists at the California Institute of Technology, led by John Preskill, began exploring what this means for quantum computers. Quantum computers use entanglement to perform calculations that classical computers cannot. They're building devices with dozens of entangled quantum bits, working toward machines with thousands or millions. Preskill realized that these quantum computers might be able to simulate holographic universes. Not just simulate them approximately, but create actual holographic spaces where the mathematics of the holographic principle applies. They started with simple systems. A quantum computer with 50 entangled qubits can create a holographic space with a few dimensions. The qubits represent the boundary, and the entanglement pattern between them creates an emergent space. By manipulating the entanglement, they can change the geometry of that space. They can create regions where space expands or contracts. They can even create situations where space tears apart and reconnects. These are real spaces, in the sense that they obey the mathematical laws of geometry and gravity, even though they exist only as patterns of entanglement in a quantum computer. This raises a disturbing question. Could our universe be a simulation running on a quantum computer? Not in the sense of a computer simulation like a video game, but in the sense that some higher dimensional reality is using quantum entanglement to create our three-dimensional space. The mathematics doesn't rule this out. In fact, the mathematics suggests it's possible. If space emerges from entanglement, then any sufficiently complex pattern of entanglement will create a space. Our universe could be the emergent space created by quantum information processing in some higher dimensional reality. But let's focus on what we can measure, what we can test. In 2018, physicists at the University of Maryland performed an experiment that demonstrated the connection between entanglement and geometry. They created a system of 7 trapped ions, electrically charged atoms held in place by electromagnetic fields. They entangled these ions in a specific pattern and showed that the entanglement structure corresponded to a particular geometry. By measuring how information spread through the system, they could reconstruct the emergent space created by the entanglement. The space wasn't physical in the usual sense. The ions were sitting in a laboratory, separated by micrometers. But the information flow between them created an abstract space with its own geometry, determined entirely by the entanglement pattern. This is what's happening in our universe, but on an incomprehensibly larger scale. The cosmic horizon contains approximately 10 to the power of 123 quantum bits of information. These bits are entangled in patterns so complex that no computer we could ever build could simulate them. And those entanglement patterns create the three-dimensional space you experience. Every atom, every particle, every point in space corresponds to a particular pattern of entanglement on the boundary. Now think about motion. When you move your hand, what's really happening? In the three-dimensional description, your hand is traveling through space, changing its position from one point to another. But in the holographic description, the quantum information representing your hand on the two-dimensional boundary is changing its entanglement pattern with the information representing the rest of the universe. Motion through space is a change in entanglement structure on the boundary. This has profound implications for the nature of time. Time, like space, might be emergent. In 2019, a physicist named Leonard Susskind proposed that the flow of time is related to the growth of quantum complexity. Quantum complexity is a measure of how difficult it is to create a particular quantum state. As a quantum system evolves, its complexity typically increases. Susskind suggested that this growth of complexity is what we experience as the passage of time. The future is the direction of increasing complexity. The past is the direction of decreasing complexity. In the holographic universe, this means that time emerges from the way entanglement patterns change on the boundary. The cosmic horizon isn't static. The quantum information encoded there is constantly evolving, becoming more complex, more entangled. And that evolution is what creates the flow of time in the three-dimensional projection. You experience time as flowing forward because the entanglement complexity on the boundary is increasing. If the complexity stopped increasing, time would stop. If the complexity decreased, time would flow backward. But here's the truly mind-bending part. The boundary itself might be timeless. Time might exist only in the projection, only in the three-dimensional space we experience. On the two-dimensional boundary, there might be no time at all, just information, organized in patterns, with no past or future. The entire history of the universe, from the Big Bang to the present moment to the distant future, might exist simultaneously on the boundary, encoded in a timeless pattern of quantum information. What we experience as the flow of time is our consciousness moving through that pattern, experiencing one moment after another. Imagine a movie stored on a DVD. The entire movie exists on the disc simultaneously. The beginning, middle, and end are all there at once. But when you play the movie, you experience it as unfolding in time. One scene follows another. Characters age, events happen in sequence. The flow of time in the movie is created by the way the information is read from the disc. Similarly, the flow of time in our universe might be created by the way information is processed in the holographic projection. The information on the boundary is timeless, but the projection creates time. In 2020, during the global pandemic, physicists had time to think deeply about these questions. A group at the Perimeter Institute for Theoretical Physics in Canada, led by Lee Smolin, developed new mathematical tools to study how time emerges in quantum gravity. They showed that in certain quantum systems, time is not fundamental. Instead, what we call time is a measure of change in the entanglement structure of the system. Different observers, with different entanglement patterns, experience different flows of time. Time is not absolute. It's observer-dependent, emerging from the quantum information available to that observer. This connects to something Einstein discovered over a century ago. Time is relative. In special relativity, time flows at different rates for observers moving at different speeds. In general relativity, time flows at different rates in different gravitational fields. A clock on a mountaintop runs faster than a clock at sea level because the gravitational field is weaker at higher altitude. Einstein showed that time is not a universal absolute flow. It's relative to the observer. The holographic principle takes this relativity even further. Time is not just relative, it's emergent. It doesn't exist at the fundamental level. It emerges from the pattern of quantum entanglement, and different patterns create different experiences of time. You experience time flowing forward at a particular rate because of the specific entanglement pattern that constitutes you. A different pattern would experience time differently. Some patterns might experience time flowing backward. Some might experience no time at all. But let's bring this back to something concrete, something you can relate to. Your memories. Right now, you have memories of the past. You remember what you did yesterday, what you did last year, what you did in childhood. Those memories feel real. They feel like records of events that actually happened. But if time is emergent, if the entire history of the universe exists simultaneously on the timeless boundary, then your memories are not records of the past. They're part of the present pattern of quantum information that constitutes you. The past doesn't exist anymore. It never existed as a separate thing. What exists is the current pattern of information, which includes what we call memories. This is similar to the way a movie works. When you watch a movie and a character remembers an earlier scene, that memory is not a record of something that happened to the character. It's part of the current frame of the movie. The earlier scene and the memory of it both exist as information on the DVD, and the movie creates the illusion that one came before the other. In our universe, your memories and the events they seem to record both exist as patterns of quantum information on the boundary, and the holographic projection creates the illusion that the events came first and the memories came later. In 2021, physicists at the University of Amsterdam performed computer simulations of holographic universes. They created simple models where a two-dimensional boundary with quantum information projects a three-dimensional space. They could watch how changes in the boundary information created events in the three-dimensional space. They could see how entanglement patterns created geometry, and they discovered something surprising. The three-dimensional space was more stable than the two-dimensional boundary. Random fluctuations in the boundary information tended to cancel out in the projection, creating a smooth, stable three-dimensional space. This might explain why our universe seems so orderly, so predictable. The laws of physics work. Objects behave consistently. Cause and effect operate reliably. But at the quantum level, at the level of the boundary, there might be chaos. Random fluctuations, quantum uncertainty, information constantly changing in unpredictable ways. The three-dimensional projection filters out that chaos, creating the stable, predictable universe we experience. The hologram is more orderly than the information it's projected from. Think about a hologram of a person. The holographic plate contains interference patterns, seemingly random variations in light intensity. But when you illuminate the plate correctly, a clear, stable, three-dimensional image appears. The image is more orderly than the interference pattern. Similarly, our three-dimensional universe might be more orderly than the quantum information on the boundary. The projection process creates order from chaos. This has implications for the arrow of time, the fact that time flows in one direction, from past to future, from order to disorder. The second law of thermodynamics says that entropy, disorder, always increases. A broken egg never spontaneously reassembles. Heat flows from hot to cold, never the reverse. This arrow of time is one of the deepest mysteries in physics. Why does time have a direction? Why can we remember the past but not the future? In the holographic universe, the arrow of time might emerge from the growth of entanglement complexity on the boundary. As the quantum information on the boundary evolves, it becomes more entangled, more complex. This growth of complexity creates the arrow of time in the projection. The future is the direction of increasing complexity. And because complexity almost always increases, it's statistically overwhelmingly likely, time almost always flows forward. The arrow of time is not a fundamental law. It's an emergent statistical phenomenon, arising from the way entanglement complexity grows on the boundary. In 2022, a breakthrough came from an unexpected direction. Physicists studying quantum error correction, techniques to protect quantum information from noise and decoherence, discovered that the mathematics of error correction is identical to the mathematics of the holographic principle. When you encode quantum information redundantly to protect it from errors, you're essentially creating a holographic code. The information is stored on a boundary, and the interior space emerges from the entanglement structure of that boundary. This wasn't just an analogy, it was a precise mathematical equivalence. This discovery suggested something profound. The universe might be a quantum error-correcting code. The information on the cosmic boundary might be encoded redundantly, protected from quantum fluctuations, and that error correction is what creates the stable three-dimensional space we experience. The laws of physics, the consistency of cause and effect, the reliability of our observations, all of this might emerge from quantum error correction happening on the boundary. Ahmed Almheri, a physicist at the Institute for Advanced Study in Princeton, led a team that explored this idea. They showed that black holes behave like quantum error-correcting codes. Information that falls into a black hole is not destroyed. It's encoded on the event horizon in a redundant, error-corrected form. And the three-dimensional interior of the black hole, the space inside the event horizon, emerges from that encoded information. The black hole is a hologram, and the hologram is an error-correcting code. If black holes work this way, maybe the entire universe works this way. Maybe the cosmic horizon is encoding information about our universe in an error-corrected form, and the three-dimensional space we inhabit emerges from that encoding. This would explain why the universe is so stable, why the laws of physics are so consistent. The error correction on the boundary filters out quantum noise, creating a clean, predictable projection. But error correction requires redundancy. The same information must be stored in multiple places, so that if one copy is corrupted, the others can be used to recover it. In the holographic universe, this means that the information about any point in three-dimensional space is not stored at just one location on the boundary. It's spread out, encoded redundantly across a large region of the boundary. The information that constitutes you is not localized to one spot on the cosmic horizon. It's distributed, entangled with information across vast regions of the boundary. This is why you can't point to a specific location on the boundary and say, "That's where I am." You're not at a location on the boundary. You're a pattern of information distributed across the boundary, and that pattern creates the experience of being a localized, three-dimensional being. The localization you experience is an illusion created by the projection. At the fundamental level, you're non-local. You're everywhere on the boundary at once, encoded in the entanglement structure. In 2023, physicists at the Kavli Institute for Theoretical Physics in Santa Barbara organized a conference on the holographic principle. Researchers from around the world gathered to share their latest findings. One of the most exciting presentations came from a team that had been studying the role of quantum entanglement in creating not just space, but also matter. They showed that particles, electrons, quarks, photons, might themselves be emergent phenomena, arising from the entanglement structure on the boundary. In this view, there are no fundamental particles. There is only quantum information on the boundary, entangled in complex patterns. Some patterns of entanglement create what we experience as particles. Other patterns create what we experience as forces. The distinction between matter and space dissolves. Both are emergent phenomena. Both arise from entanglement. Both are aspects of the holographic projection. Think about what this means for your body. You feel solid. You feel like you're made of matter, of atoms, of particles. But those particles might not be fundamental. They might be patterns of entanglement on the boundary. Your body is not made of matter in the traditional sense. Your body is a pattern of quantum information projected into 3 dimensions, creating the experience of solidity, of physicality, of being a material object. When you touch a table, you feel resistance. The table feels solid because the electrons in your hand repel the electrons in the table. But those electrons are not fundamental particles. They're patterns of entanglement on the boundary. The repulsion you feel is an interaction between entanglement patterns. The solidity of matter is an emergent property of quantum information. This raises a question that physicists are still debating. If everything is information, what is information made of? Is information fundamental, or does it emerge from something even deeper? Some physicists believe information is the most fundamental thing in the universe. Others believe there must be something beneath information, some substrate that information is made of. But nobody knows what that substrate might be. In 2024, a team at the Max Planck Institute for Gravitational Physics in Germany proposed a radical idea. Maybe information is not made of anything. Maybe information is the fundamental ontology, the basic nature of reality. In this view, asking what information is made of is like asking what existence is made of. It's a category error. Information doesn't emerge from something more fundamental. Information is the fundamental thing, and everything else, space, time, matter, energy, emerges from it. This is a philosophical shift as profound as any in the history of science. For centuries, we thought matter was fundamental. Then we discovered that matter is made of atoms. Then we discovered that atoms are made of particles. Then we discovered that particles are excitations of quantum fields. Now we're discovering that quantum fields might be patterns of information. And information might be the end of the line. The most fundamental thing. The thing that doesn't emerge from anything else. But what does it mean to say that information is fundamental? Information is always information about something. A bit is 0 or 1. A quantum bit is in a superposition of 0 and 1. But 0 and 1 are labels. They're symbols. What are they symbols for? If information is fundamental, what is it representing? Some physicists believe that at the fundamental level, information doesn't represent anything. It just is. A bit is not a symbol for something else. A bit is a fundamental unit of reality. The universe is made of bits, and those bits don't represent anything beyond themselves. They're not encoding information about some deeper reality. They are reality. This is difficult to wrap your mind around because we're used to thinking of information as being about something. A book contains information about events, people, ideas. A photograph contains information about a scene. But fundamental information is not about anything. It's the raw material of existence. The universe is not a description of reality. The universe is information, and that information is reality. In 2025, physicists began exploring what this means for consciousness. If the universe is information, and you are part of the universe, then you are information. Your thoughts, your experiences, your sense of self, all of this is information. But information is not passive. Information can be processed. Information can be organized into patterns. And some patterns of information might be conscious. This is the hard problem of consciousness. How does subjective experience arise from physical processes? How does the feeling of what it's like to see red, to feel pain, to experience joy, emerge from neurons firing in your brain? In the materialist view, consciousness is somehow produced by matter. But if matter is emergent, if matter is itself a pattern of information, then consciousness might also be a pattern of information. Not produced by information, but made of information. Your consciousness might be a particular pattern of entanglement on the cosmic boundary. The pattern is so complex, so intricately organized, that it experiences itself. It has subjective experience. It feels like something to be that pattern. And the three-dimensional body you experience yourself as inhabiting is the projection of that pattern into three-dimensional space. This suggests that consciousness is not localized in your brain. Your brain is part of the projection. The real you, the pattern of information that experiences itself as you, is distributed across the cosmic boundary. Your brain is where that pattern manifests in three-dimensional space, but the pattern itself is non-local. It's everywhere on the boundary at once. This might explain some of the mysteries of consciousness. Why does consciousness feel unified, even though your brain is made of billions of separate neurons? Maybe because the underlying pattern of information on the boundary is unified, entangled into a single, coherent structure. Why do you experience a continuous stream of consciousness, even though your brain processes information in discrete steps? Maybe because the pattern on the boundary is continuous, and the discrete processing in your brain is just how that continuous pattern manifests in the projection. These are speculations, of course. We don't have a theory of consciousness yet. We don't know how subjective experience arises from information. But the holographic principle provides a new framework for thinking about these questions. If consciousness is a pattern of information on the boundary, then understanding consciousness means understanding the structure of that pattern. It means understanding how information can be organized in such a way that it experiences itself. Let me tell you about the moment when physicists realized they might be able to test this. Not just theorize, not just calculate, but actually measure whether we live in a hologram. It was 2014, and a team at Fermilab, the Fermi National Accelerator Laboratory in Illinois, was building something that sounded like science fiction. They called it the holometer. The name comes from holography, and its purpose was audacious: to detect the graininess of space-time itself. Here's the logic. If the universe is a hologram projected from a two-dimensional surface, then space-time should not be perfectly smooth. It should be pixelated at the smallest scales, just like a digital photograph is made of pixels. The holometer was designed to detect this pixelation by measuring tiny fluctuations in the fabric of space-time. Fluctuations so small, they're at the edge of what's physically possible to measure. The device used two powerful laser beams, each traveling 40 meters back and forth in perpendicular directions. If space-time is pixelated, the laser beam should show correlated noise, tiny synchronized jitters that reveal the quantum graininess of space itself. The experiment ran for 2 years. Physicists monitored the laser beams, looking for the signature of holographic noise. And in 2015, they announced their results. No holographic noise detected. Space-time appeared smooth down to the scales they could measure. Does this disprove the holographic principle? No. It means that if space-time is pixelated, the pixels are smaller than the holometer could detect. The cosmic horizon is so far away, 46 billion light-years, that the pixelation might be far too fine for any Earth-based experiment to measure. But the fact that physicists tried, the fact that they built a machine to test this idea, shows how seriously the scientific community takes the holographic principle. And there are other ways to test it. In 2017, physicists realized that gravitational waves, ripples in space-time caused by colliding black holes, might carry signatures of holographic structure. When two black holes merge, they create violent distortions in space-time that propagate outward at the speed of light. We've detected these gravitational waves using LIGO, the Laser Interferometer Gravitational Wave Observatory. The waves match Einstein's predictions with extraordinary precision. But if space-time is holographic, there might be tiny deviations from Einstein's predictions, subtle anomalies in the waveforms that reveal the underlying holographic structure. Teams of physicists are now analyzing gravitational wave data, looking for these anomalies. They're comparing thousands of black hole collisions, searching for patterns that don't quite fit classical general relativity. So far, they haven't found anything definitive, but the search continues. Every new gravitational wave detection is another opportunity to test whether space-time is a projection from a distant boundary. But let's talk about what we do know, what the mathematics tells us with certainty. The holographic principle places fundamental limits on information density. This is called the Bekenstein bound, named after Jacob Bekenstein, who first calculated it. The bound says that the maximum amount of information that can be contained in any region of space is proportional to the surface area of that region, measured in Planck units. 1 bit of information per Planck area. This is not a technological limit. This is not something we might overcome with better engineering. This is a fundamental law of physics, as absolute as the speed of light. Think about what this means for computation. Right now, the most powerful supercomputers can perform about 10 to the power of 18 operations per second. That's a quintillion calculations per second. Engineers are working toward exascale computing, 10 to the power of 18 operations per second sustained over time. But there's an ultimate limit. If you tried to build a computer that stores and processes more information than the Bekenstein bound allows, it would collapse into a black hole. The information density would become so great that it would warp space-time catastrophically. In 2019, a physicist named Seth Lloyd at MIT calculated the ultimate laptop, the most powerful computer that could theoretically exist within the laws of physics. He assumed a 1-kilogram computer, about the mass of a laptop, and calculated how much information it could store and how fast it could process that information before collapsing into a black hole. The answer? It could store about 10 to the power of 31 bits and perform about 10 to the power of 51 operations per second. That's incomprehensibly fast, 10,000 trillion operations per second. But it's still finite. There's a limit, imposed by the holographic principle, on how much computation can happen in a given volume of space. This limit applies to everything. Your brain is a computer, processing information through neural connections. The Bekenstein bound places an upper limit on how much information your brain could theoretically process. That limit is so high, far beyond what your actual neurons can do, that it's not a practical constraint. But it's there. The universe itself is processing information, evolving from one quantum state to another. The Bekenstein bound limits how much information the universe can process. The cosmic horizon has a finite surface area, which means the universe has a finite information capacity, about 10 to the power of 123 bits, as we discussed earlier. But here's something that will make you uncomfortable. If the universe has finite information capacity, then there are only a finite number of possible states the universe can be in. It's an incomprehensibly large number. 10 to the power of 10 to the power of 123 possible states. But it's finite. This means that if the universe existed for long enough, it would eventually cycle through all possible states and return to a state it had been in before. The universe would repeat itself. This is called the Poincaré recurrence time, named after the mathematician Henri Poincaré, who first calculated it for simple systems. For the universe, the recurrence time is unimaginably long, 10 to the power of 10 to the power of 123 years. That's not 10 to the power of 123 years. That's 10 to the power of 10 to the power of 123 years. A 1 followed by 10 to the power of 123 zeros years. To put this in perspective, the current age of the universe is about 14 billion years. The Poincaré recurrence time is so much longer that the age of the universe is effectively zero in comparison. But in principle, if you waited long enough, the universe would return to exactly the state it's in right now. Every atom would be in the same position. Every particle would have the same momentum. You would be sitting here, reading these words, having these thoughts, exactly as you are now. And this would happen not just once, but infinitely many times, because time is infinite, but the number of possible states is finite. This is deeply disturbing. It means that everything that has ever happened will happen again. Everything you've ever done, you'll do again. Every choice you've ever made, you'll make again. Not because of fate or destiny, but because of mathematics. Because the universe has finite information capacity and infinite time. You are trapped in an eternal recurrence, living the same life over and over, forever. Unless the universe doesn't last forever. Unless the expansion of the universe continues accelerating, as current observations suggest, until space-time itself tears apart in what's called the Big Rip. Or unless the universe eventually collapses in a big crunch. Or unless something else happens that we haven't predicted. The mathematics of eternal recurrence assumes the universe continues in a steady state forever. But we don't know if that's true. And there's another possibility, one that's even stranger. What if the holographic principle means that the universe is already repeating, but we can't tell? Remember, all the information about the universe is encoded on the two-dimensional cosmic horizon. The three-dimensional space we experience is a projection. Now imagine that the information on the horizon is periodic. It repeats after some interval. The projection would also repeat. The entire history of the universe would cycle. But because we're inside the projection, we'd have no way to detect it. Our memories would reset with each cycle. We'd experience each cycle as if it were the first and only time. This is not just philosophical speculation. In 2020, a team of physicists at the University of Cambridge explored this possibility mathematically. They showed that certain holographic universes can have periodic boundary conditions. The information on the boundary repeats after a certain interval. The three-dimensional projection of such a universe would be indistinguishable from a non-periodic universe to any observer inside it. You could be living in a repeating universe right now, and you'd never know. But let's step back from these cosmic questions and talk about something more immediate: black holes. Black holes are the key to understanding the holographic principle, because they're the places where the principle is most obvious, most testable. When matter falls into a black hole, it crosses the event horizon and disappears from our view. But according to the holographic principle, the information about that matter is not lost. It's encoded on the event horizon. The black hole's entropy, its information content, increases by an amount proportional to the surface area added to the event horizon. Stephen Hawking famously argued that information is destroyed when it falls into a black hole, because black holes evaporate through Hawking radiation, and that radiation is thermal. It carries no information about what fell in. This led to the black hole information paradox. If information is destroyed, quantum mechanics is violated. If information is preserved, we need to explain how it gets out of the black hole. Physicists argued about this for decades. The holographic principle resolves the paradox. Information is not destroyed. It's encoded on the event horizon. When the black hole evaporates, the information is released in the Hawking radiation. But here's the strange part. The information is encoded in correlations between different parts of the radiation. No single particle of Hawking radiation carries information about what fell into the black hole. The information is spread out, entangled across many particles. You'd need to collect and analyze a large fraction of the Hawking radiation to decode the information about what fell in. In 2019, a team led by Jeff Pennington at Stanford University made a breakthrough in understanding how this works. They calculated exactly how information escapes from an evaporating black hole. They showed that there's a critical moment, when the black hole has evaporated to about half its original mass, when the information starts to come out faster than it went in. Before this moment, the Hawking radiation is mostly thermal, carrying little information. After this moment, the radiation becomes increasingly correlated, carrying more and more information about the black hole's interior. By the time the black hole completely evaporates, all the information has been released. This is called the Page curve, named after physicist Don Page, who first predicted its shape in the 1990s. Pennington's team calculated the Page curve using the mathematics of the holographic principle and showed that it matches what quantum mechanics requires. Information is preserved. The paradox is resolved. But the resolution requires accepting that information is encoded holographically on the event horizon. Now here's where it gets personal. If black holes encode information holographically, and if the universe as a whole is holographic, then you are encoded on the cosmic horizon in the same way that matter falling into a black hole is encoded on the event horizon. Your information is spread out, entangled across a vast region of the boundary. And just as information can escape from a black hole through Hawking radiation, your information could theoretically be reconstructed from the cosmic horizon. This raises a question that sounds like science fiction, but is actually serious physics. Could you be copied? If all the information that constitutes you is encoded on the cosmic horizon, could that information be read and used to create a duplicate of you? Not a clone. A clone shares your DNA, but has different experiences, different memories. A true duplicate, with all your memories, all your thoughts, all your experiences, identical down to the quantum state of every particle. The mathematics says yes, in principle. If you could access the information on the cosmic horizon, if you could decode the holographic pattern that represents you, you could reconstruct that pattern elsewhere. You could create a duplicate. But there are practical problems. First, the cosmic horizon is 46 billion light-years away. You can't access it. Second, the information is encoded in quantum states, and quantum mechanics says you can't copy quantum states. This is called the no-cloning theorem. You can move quantum information from one place to another, but you can't duplicate it. But wait. The no-cloning theorem applies to quantum information in three-dimensional space. Does it apply to information on the two-dimensional boundary? Some physicists argue that it doesn't. The boundary is not a quantum system in the usual sense. It's the substrate from which quantum systems emerge. The rules might be different there. If so, then copying might be possible at the boundary level, even if it's impossible in the three-dimensional projection. This is deeply unsettling. It means that there might be multiple copies of you, encoded in different regions of the cosmic horizon, each projecting into three-dimensional space as a separate individual. You might not be unique. There might be other versions of you, living other lives, having other experiences, all arising from the same fundamental pattern of information on the boundary. In 2021, a philosopher named David Chalmers wrote a paper exploring the implications of the holographic principle for personal identity. He argued that if you are a pattern of information on the boundary, then what makes you is not your physical body, not your location in space, but the structure of that information pattern. If the pattern is copied, the copy is also you. Not a different person who happens to be identical to you, but literally you, experiencing itself in two places at once. This is the opposite of how we usually think about identity. We think of ourselves as unique individuals, located at specific points in space and time. But if the holographic principle is correct, you are not located anywhere. You are a pattern of information distributed across the cosmic horizon, and that pattern creates the experience of being a localized individual. The localization is an illusion. The uniqueness might also be an illusion. But let's talk about something we can actually test, something that might happen in our lifetimes: quantum computers. We mentioned earlier that quantum computers can simulate holographic universes. As quantum computers become more powerful, they'll be able to simulate larger and more complex holographic spaces. In 2023, Google's quantum computing team announced that they had simulated a holographic universe with 64 qubits. The universe was tiny, just a few dimensions, with simple dynamics. But it was a real holographic universe, obeying the mathematics of the ADS-CFT correspondence. They could manipulate the qubits on the boundary and watch how the interior space responded. They could create particles, make them interact, observe how information spread through the space. And they confirmed that the information in the interior was bounded by the surface area of the boundary, exactly as the holographic principle predicts. This was not a simulation of a holographic universe. This was an actual holographic universe, existing as a pattern of quantum entanglement in the quantum computer. Now imagine scaling this up. Current quantum computers have hundreds of qubits. Within a decade, we might have quantum computers with millions of qubits. With millions of qubits, you could simulate holographic universes large enough to contain complex structures, maybe even structures complex enough to be conscious. You could create artificial universes populated by artificial beings, all existing as patterns of entanglement in a quantum computer. This raises an ethical question that physicists are starting to take seriously. If you create a conscious being in a simulated holographic universe, do you have moral obligations to that being? The being would experience itself as real. It would have thoughts, feelings, experiences. It would suffer if you caused it pain. It would die if you turned off the computer. Is it ethical to create such beings? Is it ethical to experiment on them? Is it ethical to delete them? In 2024, a group of physicists and philosophers at Oxford University published a paper arguing that we need to develop ethical guidelines for holographic simulations before the technology becomes powerful enough to create conscious beings. They proposed that any simulated being with sufficient complexity to be potentially conscious should be treated with the same moral consideration as a biological being. This is controversial. Many scientists argue that simulated beings are not truly conscious, that consciousness requires biological substrate. But if consciousness is a pattern of information, as the holographic principle suggests, then substrate shouldn't matter. A conscious pattern in a quantum computer is just as conscious as a conscious pattern in a biological brain. And here's the disturbing corollary. If we can create conscious beings in holographic simulations, then we might be conscious beings in a holographic simulation. Not a simulation in the sense of a computer program running on a classical computer, but a holographic projection from a higher dimensional boundary. Some advanced civilization might have created our universe as a holographic simulation, and we'd have no way to tell. The physics would be the same. The mathematics would be the same. Everything we measure would be consistent with being in a holographic projection, whether that projection is the fundamental nature of reality or an artificial creation. This is called the simulation hypothesis, and it's been around for decades. But the holographic principle gives it new weight. If universes are holographic projections, then creating universes is a matter of manipulating quantum information on a boundary. Any sufficiently advanced civilization could do it. And if civilizations can create universes, then most universes are probably created rather than fundamental. The odds are that we're in a created universe rather than the original one. But let's be clear, this is speculation. We have no evidence that we're in a simulation. We have no evidence that other universes exist. What we do have is mathematics. The mathematics of the holographic principle is solid, tested, confirmed by thousands of calculations and computer simulations. The mathematics says that information in any volume of space is bounded by the surface area of that volume. The mathematics says that space emerges from quantum entanglement. The mathematics says that our three-dimensional universe could be a projection from a two-dimensional boundary. Whether that boundary is the cosmic horizon of a fundamental universe or the boundary of a simulated universe created by some higher dimensional civilization, the mathematics doesn't tell us. Both possibilities are consistent with what we observe, and that's unsettling. It means we might never know whether our universe is fundamental or simulated. The question might be unanswerable, not because we lack the technology to investigate it, but because the two possibilities are mathematically equivalent. In 2025, a team at the Perimeter Institute proposed a way to test this. They argued that if our universe is a simulation, there might be computational limits that show up as anomalies in physical laws. Just as the holometer looked for pixelation in spacetime, we could look for computational artifacts, places where the simulation cuts corners, where the physics is approximate rather than exact. They proposed specific experiments to look for these artifacts in high-energy particle collisions and in the cosmic microwave background radiation. The experiments haven't been done yet. They require technology we don't have, but they're theoretically possible. Within a few decades, we might be able to test whether our universe shows signs of being a computation. And if we find such signs, it would be the most profound discovery in human history. It would mean that reality is not what we thought. It would mean that we are not what we thought. It would mean that everything we experience is a projection, a simulation, a holographic image created by information processing on a distant boundary. But even if we never find such evidence, even if our universe turns out to be fundamental rather than simulated, the holographic principle has already changed everything. It has changed how we think about space. It has changed how we think about time. It has changed how we think about information, matter, energy, consciousness. It has revealed that the universe is stranger than we imagined, stranger than we could have imagined. You are not a collection of atoms arranged in space. You are a pattern of quantum information encoded on a two-dimensional surface at the edge of the universe. That pattern is so complex, so intricately entangled, that it creates the experience of being a three-dimensional being, living in three-dimensional space, moving through time. The experience is real. The thoughts you're thinking right now are real. The emotions you feel are real. But the substrate, the fundamental nature of what you are, is not what you think it is. You are a hologram, and so is everything else. The stars you see at night are holograms. The ground beneath your feet is a hologram. The atoms in your body are holograms. All of it, every particle, every force, every interaction, emerges from information encoded on a distant, two-dimensional surface. The three-dimensional world you experience is a projection, and the projection is so perfect, so seamless, that you never notice the underlying reality. But now you know. And knowing changes everything. It changes how you see the world. It changes how you see yourself. Every time you look at your hand, you'll remember, this hand is a projection. Every time you feel solid ground beneath your feet, you'll remember, this solidity is emergent. Every time you experience the passage of time, you'll remember, time is not fundamental. The holographic principle is not just a theory about physics. It's a theory about the nature of existence itself. It tells us that reality is not what it appears to be. It tells us that the universe is information, organized in patterns, projected into the experience we call reality. And it tells us that we are part of that information, part of that pattern, part of that projection. You are the universe experiencing itself. Not metaphorically, literally. The information that constitutes you is part of the information that constitutes the universe. There is no boundary between you and the cosmos. You are not in the universe. You are the universe, localized into a pattern that experiences itself as a separate individual. But the separation is an illusion. At the fundamental level, you are continuous with everything else. You are entangled with the cosmic horizon. You are the hologram, and the hologram is you. This is what physics has discovered. This is what the mathematics tells us. This is the reality we live in, whether we understand it or not, whether we accept it or not. The universe is a hologram. You are a projection from the edge of the universe. And everything you thought you knew about reality was wrong. But here's the final twist, the thing that will keep you awake tonight. If the universe is a hologram, then the boundary, The cosmic horizon where the information is encoded is also part of the universe. The boundary is not outside the universe, it's part of the universe, which means the universe contains the information that defines the universe. The universe is self-referential. It's a strange loop, a system that contains a description of itself. This is similar to a computer program that can modify its own code, or a book that contains instructions for writing the book, or a mind that can think about its own thoughts. Self-reference creates paradoxes, infinite regresses, strange loops. And the universe is the ultimate strange loop. It contains the information that defines it. It projects itself from its own boundary. It experiences itself through conscious beings like you. You are the universe looking at itself. You are the hologram examining the holographic plate. You are the projection studying the boundary. And in doing so, you are changing the very thing you're studying. Because observation is interaction, and interaction changes quantum states. When you observe the universe, you're not passively receiving information. You're actively participating in the creation of reality. This is what quantum mechanics has been telling us for a century. The observer is not separate from the observed. Measurement is not passive. Reality is not independent of observation. And the holographic principle takes this even further. If you are a pattern of information on the cosmic boundary, and if observation changes quantum states, then your observations are changing the pattern that constitutes you. You are creating yourself through the act of observation. This is the deepest mystery of all. Not just that the universe is a hologram, but that the hologram is self-creating. The information on the boundary is not static. It's evolving, changing, becoming more complex. And that evolution is driven by observation, by measurement, by conscious beings like you interacting with the universe. You are not just experiencing reality, you are creating it. Every choice you make, every observation you perform, every thought you think, all of this changes the quantum state of the universe. All of this changes the pattern of information on the cosmic boundary. All of this changes the holographic projection we call reality. You are not a passive observer. You are an active participant in the creation of the universe. And if that's true, then the future is not determined. The information on the boundary is not fixed. It's evolving, and you are part of that evolution. Your choices matter, your observations matter, your consciousness matters. Not because of some mystical connection to the universe, but because of physics, because of the holographic principle. Because you are the universe, and the universe is you. This is the ultimate implication of the holographic principle. Not just that reality is a projection, but that you are the projector. Not just that the universe is information, but that you are processing that information. Not just that consciousness is a pattern, but that the pattern is creating itself through the act of being conscious. You are a hologram, but you are also the light that illuminates the hologram. You are the projection, but you are also the source of the projection. You are the universe experiencing itself, creating itself, becoming itself. And that is the most profound truth physics has ever discovered. I understand perfectly what you're thinking right now. You're thinking, this sounds like pseudoscience. This sounds like the kind of wild speculation that belongs in late-night documentaries about ancient aliens and consciousness crystals, not in serious physics. And I want to acknowledge that feeling, because it's the right instinct. Skepticism is how science protects itself from nonsense. Skepticism is what separates physics from fantasy. So let me be absolutely clear about what we know and what we don't know. We know, with mathematical certainty, that black holes have entropy proportional to their surface area. This has been calculated, verified, confirmed by thousands of independent physicists. We know that the ADS-CFT correspondence is mathematically exact for certain types of universes. We know that quantum entanglement creates geometric connections in space-time. These are not speculations. These are proven mathematical facts. But here's what we don't know. We don't know if our universe is actually holographic. The mathematics works for abstract universes, for black holes, for simplified models. But our universe is not simple. Our universe has matter, radiation, dark energy, cosmic expansion. We don't have a complete holographic description of our actual universe. We have pieces, fragments, hints. We have mathematical structures that suggest holography is fundamental. But we don't have proof. We don't know where the boundary is. I've been saying it's at the cosmic horizon, 46 billion light-years away. But that's an assumption. The cosmic horizon is moving. It's getting farther away as the universe expands. Does the boundary move with it? Is the boundary even a physical surface, or is it an abstract mathematical construct? We don't know. We don't know how consciousness fits into this picture. I've suggested that consciousness might be a pattern of information on the boundary, but that's speculation. We don't have a theory of consciousness. We don't know how subjective experience arises from physical processes, whether those processes are neurons firing or quantum bits entangling. The hard problem of consciousness remains unsolved. We don't know if we're in a simulation. The mathematics allows for it, but mathematics allows for many things that don't exist. We have no evidence, no test, no way to distinguish a fundamental holographic universe from a simulated one. The question might be meaningless. And here's the most important thing we don't know. We don't know what information is. I've been treating information as fundamental, as the basic substance of reality. But what is information really? Is it physical? Is it abstract? Is it something else entirely? Physicists argue about this. Philosophers argue about this. Nobody has a satisfactory answer. So why am I telling you all this? Why spend an hour explaining a theory that might be wrong, that has gaps, that makes claims we can't verify? Because even if the holographic principle turns out to be incomplete, even if our universe is not exactly holographic in the way I've described, the principle has already taught us something profound about the nature of reality. It has taught us that space is not fundamental. Whether or not our universe is a hologram, the mathematics proves that space can emerge from quantum entanglement. Space can be a derived property, not a basic one. This is revolutionary. For thousands of years, humans have assumed that space is the stage on which events happen. But space might be an event itself, something that emerges from deeper structures. It has taught us that information has physical consequences. Information is not just an abstract concept. Information has entropy. Information has energy. Information warps space-time. The universe is not just described by information. The universe is made of information. In some deep sense, we're still trying to understand. It has taught us that the universe is stranger than we imagined. Every time we think we've figured out reality, we discover another layer of strangeness. Atoms are mostly empty space. Particles are waves. Time is relative. Space is curved. And now, space might be a hologram. Each discovery reveals that our intuitions about reality are wrong. The universe doesn't care about our intuitions. But let's talk about what comes next. Where does physics go from here? What are the open questions, the frontiers, the mysteries we're trying to solve? First, quantum gravity. We have two great theories of physics, quantum mechanics and general relativity. Quantum mechanics describes the very small, atoms, particles, fields. General relativity describes the very large, planets, stars, galaxies, the curvature of space-time. Both theories are extraordinarily successful. Both make predictions that have been verified to incredible precision. But they're incompatible. They use different mathematics, different assumptions, different concepts of what reality is. The holographic principle is a clue about how to unify them. It suggests that quantum mechanics is more fundamental than general relativity, that space-time and gravity emerge from quantum information. But we don't have the complete theory yet. We don't have equations that describe quantum gravity in our universe. String theory is one attempt. Loop quantum gravity is another. The holographic principle is a third approach. But none of them are complete. None of them make predictions we can test with current technology. Physicists are working on this. Right now, at universities and research institutes around the world, thousands of brilliant minds are trying to solve quantum gravity. They're developing new mathematical tools, running computer simulations, proposing experiments. Progress is slow because the energy scales involved are so high. The Planck energy, where quantum gravity becomes important, is about 10 to the power of 19 times higher than anything we can create in particle accelerators. We can't do experiments at those energies. We have to rely on mathematics, on thought experiments, on indirect evidence. But there are ways forward. Gravitational waves give us a new window into extreme physics. Black hole mergers create conditions where space-time is violently curved, and quantum effects might be detectable. The Event Horizon Telescope, which took the first image of a black hole in 2019, is being upgraded to capture more detailed images, to study the region near the event horizon where holographic effects might be visible. Quantum computers are another tool. As quantum computers become more powerful, we'll be able to simulate larger holographic universes, test predictions, explore scenarios that are impossible to calculate by hand. Google, IBM, and other companies are racing to build quantum computers with thousands of qubits. Within a decade, we might have machines powerful enough to simulate holographic universes with complex dynamics, maybe even complex enough to test whether consciousness can emerge from holographic patterns. Second, dark energy. The universe is expanding, and the expansion is accelerating. Something is pushing space apart, and we don't know what it is. We call it dark energy, but that's just a name for our ignorance. Dark energy makes up about 68% of the universe's energy content. It's the dominant component of reality, and we have no idea what it is. The holographic principle might help. Some physicists think dark energy is related to the cosmic horizon. As the universe expands, the cosmic horizon gets farther away, and its surface area increases. If information is encoded on that surface, then the amount of information in the universe is increasing. Maybe dark energy is the force that drives this increase. Maybe the expansion of the universe is driven by the growth of information. This is speculative, but it's testable. If dark energy is related to holographic information, then its properties should change in specific ways as the universe expands. Astronomers are measuring dark energy with increasing precision, using supernovae, galaxy surveys, gravitational lensing. Within a few years, we'll have data precise enough to test whether dark energy behaves the way holographic models predict. Third, the beginning of the universe. The Big Bang is not the beginning of time. It's the beginning of our current expansion phase. But what came before? Was there a before? Did time exist before the Big Bang? Or did time itself begin at the Big Bang? These questions are at the edge of what physics can address. The holographic principle suggests a new way to think about this. If time is emergent, if time arises from the evolution of quantum information on the boundary, then asking what came before the Big Bang might be like asking what's north of the North Pole. The question assumes time extends infinitely into the past, but maybe it doesn't. Maybe time has a beginning, not because something caused it to start, but because the concept of before doesn't apply beyond a certain point. Some physicists are exploring this idea. They're developing models where the universe begins as a quantum fluctuation in a timeless state. The fluctuation creates a pattern of information on a boundary, and that pattern evolves, becoming more complex, creating the experience of time. The Big Bang is not the creation of the universe from nothing. It's the moment when quantum information became complex enough to create time. This is deeply strange, and it might be wrong. But it's the kind of strangeness that physics has encountered before. Relativity seemed strange when Einstein proposed it. Quantum mechanics seemed strange when Bohr and Heisenberg developed it. The expansion of the universe seemed strange when Hubble discovered it. Strangeness is not a reason to reject an idea. Strangeness is often a sign that we're onto something real. Fourth, the nature of consciousness. I've talked about consciousness as if it's a pattern of information, but I've been vague about the details because we don't have the details. We don't know how consciousness works. We don't know why some physical systems are conscious and others aren't. We don't know what it feels like to be a bat, or an octopus, or an artificial intelligence. We don't even know if those questions have answers. The holographic principle doesn't solve the hard problem of consciousness, but it reframes it. If consciousness is a pattern of information, then understanding consciousness means understanding what kinds of patterns are conscious. This is a question we can investigate. We can study the information processing in brains, in computers, in quantum systems. We can look for common features, for principles that distinguish conscious patterns from unconscious ones. Some researchers are doing this. Giulio Tononi at the University of Wisconsin has developed a theory called integrated information theory, which proposes that consciousness is a measure of how integrated a system's information is. The more integrated, the more conscious. This theory makes testable predictions about which systems should be conscious and which shouldn't. It's controversial, but it's a start. Others are exploring quantum theories of consciousness, the idea that consciousness involves quantum processes in the brain. Roger Penrose and Stuart Hameroff have proposed that microtubules in neurons perform quantum computations that give rise to consciousness. This is even more controversial, and most neuroscientists are skeptical. But if consciousness is fundamentally quantum, if it's a pattern of quantum information on the holographic boundary, then quantum processes in the brain might be how that pattern manifests in three-dimensional space. We don't know, and that's okay. Science is not about having all the answers. Science is about asking better questions, developing better tools, making progress toward understanding. We've made enormous progress in understanding the universe over the past century. We've discovered that space is curved, that time is relative, that particles are waves, that the universe is expanding, that black holes exist, that quantum entanglement is real. Each discovery seemed impossible before we made it. Each discovery revealed that reality is stranger than we thought. The holographic principle is the latest in this series of strange discoveries, and it won't be the last. There are mysteries we haven't even imagined yet, questions we don't know how to ask, phenomena we haven't observed. The universe is vast, ancient, complex beyond comprehension. We've barely begun to understand it. But here's what I want you to take away from this. The fact that we can understand anything at all is miraculous. The fact that the universe is comprehensible, that it follows mathematical laws, that we can discover those laws through observation and experiment, this is not obvious. It's not guaranteed. It's a profound mystery in itself. Why does the universe follow laws? Why is mathematics so effective at describing reality? Why can human brains, evolved to hunt and gather on the African savanna, understand quantum mechanics and general relativity and the holographic principle? These are deep questions, and we don't have answers. But the fact that we can ask them, the fact that we can make progress toward answering them, is extraordinary. You are part of this. You, watching this video, thinking these thoughts, experiencing this moment, you are the universe trying to understand itself. Your consciousness, your curiosity, your capacity for wonder, these are not separate from the universe. They are expressions of the universe. The universe is not a dead mechanical thing. The universe is alive with consciousness, with intelligence, with the drive to understand. And maybe that's the deepest implication of the holographic principle. Not just that you are a hologram, but that you are a hologram that knows it's a hologram. You are a pattern of information that has become aware of itself, that can study itself, that can change itself. You are the universe waking up, looking around, asking, "What am I? Where did I come from? What does it all mean?" We don't have final answers to those questions. We might never have final answers. But we have something better. We have the ability to investigate, to explore, to discover. We have science. We have mathematics. We have the collective intelligence of humanity, working together across generations to understand reality. The holographic principle is one piece of that understanding. It tells us that space is emergent, that information is fundamental, that the universe is stranger than we imagined. But it also tells us that we can understand that strangeness. We can write equations that describe it. We can build experiments that test it. We can create technologies based on it. Quantum computers are already using the principles of quantum entanglement that underlie holography. Gravitational wave detectors are already probing the structure of space-time. Telescopes are already observing the cosmic horizon. We're not just theorizing about the holographic universe. We're beginning to interact with it, to manipulate it, to use it. In the coming decades, we'll learn more. We'll develop better theories, build better experiments, make new discoveries. Maybe we'll confirm that our universe is holographic. Maybe we'll discover that it's something else, something even stranger. Either way, we'll understand reality more deeply than we do now. And you can be part of this. You don't need to be a physicist to contribute to human understanding. You can support science education, fund research, communicate discoveries to the public. You can raise children who are curious about the universe. You can vote for leaders who value truth and evidence. You can live your life with wonder, with curiosity, with the recognition that reality is strange and beautiful and worth understanding. Because here's the final truth. The holographic principle is not just about physics. It's about what it means to be human. It's about our place in the universe. It's about the relationship between mind and matter, between consciousness and cosmos, between the observer and the observed. For thousands of years, humans have told stories about our place in the universe. We've imagined ourselves at the center, with the stars revolving around us. We've imagined ourselves as special creations, separate from nature. We've imagined ourselves as accidents, meaningless fluctuations in a vast, indifferent cosmos. The holographic principle suggests something different. It suggests that we are neither central nor accidental. We are emergent. We are patterns of information that have become complex enough to experience themselves, to understand themselves, to change themselves. We are the universe becoming conscious of itself. This is not mysticism, this is physics. The mathematics says that consciousness is a pattern of information. The mathematics says that information is fundamental. The mathematics says that you are a hologram projected from the edge of the universe. And the mathematics says that the hologram is self-aware, self-creating, self-transforming. You are not separate from the universe. You are the universe, experiencing itself from a particular perspective at a particular moment in time. And every other conscious being is also the universe, experiencing itself from a different perspective. We are all holograms, all projections from the same boundary, all patterns in the same cosmic information field. This means that when you look at another person, you're not looking at something separate from yourself. You're looking at another version of yourself, another pattern in the same hologram. The boundaries between us are illusions created by the projection. At the fundamental level, we are continuous, entangled, unified. This has implications for how we treat each other, how we treat the planet, how we think about our future. If we are all patterns in the same holographic universe, then harming others is harming ourselves. Destroying the environment is destroying the substrate that creates us. Our individual actions matter because they change the pattern, and the pattern is all of us. But I don't want to end with prescriptions or moral lessons. I want to end with wonder. With the recognition that we live in a universe far stranger than our ancestors could have imagined. A universe where space is emergent, where time is relative, where particles are entangled across vast distances, where black holes encode information on their surfaces, where the entire cosmos might be a holographic projection from a two-dimensional boundary. This is the universe we inhabit. This is the reality we're part of. And the fact that we can understand any of this, the fact that we can write equations describing holography and quantum entanglement and the emergence of space-time, this is the greatest miracle of all. You are a hologram. But you are a hologram that can understand holography. You are a pattern of information that can study information theory. You are the universe that has become aware of itself. And that awareness changes everything. Because once you know you're a hologram, you can never see reality the same way again. Every solid object becomes a projection. Every distance becomes a measure of entanglement. Every moment becomes a slice through a timeless pattern. The world doesn't change, your perception of it changes. And that change in perception is itself a change in the hologram, because you are part of the hologram. This is the strange loop at the heart of existence. You are studying the universe, and the universe is you. You are changing your understanding, and that change is changing the universe. You are the observer and the observed, the hologram and the light that illuminates it, the pattern and the consciousness that experiences the pattern. Welcome to the holographic universe. Welcome to the reality where information is fundamental, where space is emergent, where consciousness is a pattern that knows itself. Welcome to the universe that is stranger than you imagined, stranger than you could imagine. Welcome to the truth. You are a three-dimensional projection from the edge of the universe. You are a hologram. And now you know it. What you do with that knowledge is up to you. But let me tell you what keeps physicists awake at night. Not the answers we've found, but the questions we can't answer. Not the mathematics that works, but the mathematics that breaks down. Not what we understand about the holographic universe, but what we fundamentally, perhaps permanently, cannot know. Here's the first question, and it's the most disturbing. Is the holographic principle actually true for our universe, or is it just mathematically beautiful? We have proof that it works for certain abstract spaces, the ADS spaces in string theory. We have proof that it works for black holes. We have computer simulations showing it works for toy universes. But our universe is not ADS space. Our universe has positive cosmological constant, not negative. Our universe is expanding, accelerating, becoming less dense. Does holography still apply? The honest answer is, we don't know. We have hints, suggestions, mathematical structures that point toward yes, but we don't have proof. We don't have a complete holographic description of our actual universe. Every physicist working on this will tell you the same thing. We're missing something fundamental. There's a piece of the puzzle we haven't found yet. And here's what makes it worse. We might never find it. The cosmic horizon is receding. As the universe expands, the boundary gets farther away, and the information density on that boundary decreases. In the far future, trillions of years from now, the cosmic horizon will be so far away that the holographic description might become meaningless. The universe might transition from a holographic phase to something else, something we don't have mathematics for yet. Second question, what is the boundary made of? I've been talking about information encoded on a two-dimensional surface. But what is that surface? Is it physical? Is it made of something? Or is it purely mathematical, an abstract construct that helps us organize our equations but doesn't correspond to anything real? Some physicists think the boundary is physical, that there's an actual two-dimensional structure at the cosmic horizon, made of quantum degrees of freedom, perhaps strings or loops, or something we haven't discovered yet. Others think the boundary is emergent, that it arises from the way we describe physics, but isn't a thing in itself. And still others think the question is meaningless, that asking what the boundary is made of is like asking what the number 7 is made of. It's a category error. We don't know. And the mathematics doesn't tell us. The mathematics describes relationships between the boundary and the bulk, between two-dimensional information and three-dimensional space. But it doesn't tell us what the boundary fundamentally is. Third question, where does quantum mechanics come from? The holographic principle assumes quantum mechanics. It uses quantum entanglement, quantum information, quantum states. But quantum mechanics itself is mysterious. Why does the universe obey quantum laws? Why is reality probabilistic at the fundamental level? Why does measurement collapse the wave function? These are questions we've been asking for a century, and we still don't have satisfying answers. Some physicists hope that holography will explain quantum mechanics, that quantum behavior will emerge from something deeper, some structure on the boundary that gives rise to quantum laws in the projection. But so far, this hasn't happened. Holography uses quantum mechanics. It doesn't explain it. We've pushed the mystery back one level, but the mystery remains. And here's a possibility that's even more unsettling. Maybe quantum mechanics is fundamental. Maybe there's no deeper explanation. Maybe the universe is quantum at its core, and asking why is like asking why existence exists. Some questions might not have answers. Fourth question, what about the other horizons? The cosmic horizon is not the only boundary in the universe. Every black hole has an event horizon. Every accelerating observer has a Rindler horizon. Every region of space has boundaries. Are all of these holographic? Is information encoded on all of them? And if so, how do these different holographic descriptions relate to each other? This is called the horizon complementarity problem, and it's deeply confusing. If you fall into a black hole, you cross the event horizon and continue falling toward the singularity. From your perspective, nothing special happens at the horizon. But from the perspective of someone outside the black hole, you never cross the horizon. You appear to freeze at the surface, your information encoded holographically on the event horizon. Both descriptions are supposed to be valid, but they seem contradictory. How can you both cross the horizon and not cross it? Physicists have proposed solutions: black hole complementarity, firewalls, ER equals EPR. But none of these solutions are completely satisfying. They all involve strange features, paradoxes, assumptions that make us uncomfortable. The horizon complementarity problem remains unsolved. Fifth question: what is time really? I've said that time is emergent, that it arises from the evolution of quantum complexity on the boundary. But this raises more questions than it answers. If time is emergent, what drives the emergence? What makes complexity increase? Why does time flow in one direction and not the other? Why do we remember the past, but not the future? The second law of thermodynamics says entropy increases, and we experience this increase as the arrow of time. But why does entropy increase? The fundamental laws of physics are time-symmetric. They work the same forward and backward. The arrow of time is not in the laws themselves. It's in the initial conditions, in the fact that the universe started in a low entropy state at the Big Bang. But why did it start that way? Why was the early universe so orderly? Some physicists think this is related to holography, that the low entropy of the early universe is a consequence of the holographic structure of the cosmic horizon. But we don't have a complete theory. We don't understand why time has an arrow, why the universe evolves from past to future, why we experience time as flowing. And here's the deepest mystery. If time is emergent, if the boundary is timeless, then the entire history of the universe exists simultaneously on the boundary. Past, present, and future are all encoded in the same timeless pattern. But we experience time as flowing. We experience the present moment as special, as different from the past and future. Why? What creates this experience of flow, of becoming, of time passing? This is called the problem of the now, and it's one of the hardest problems in physics and philosophy. We don't have an answer. We don't even have a good framework for thinking about it. Sixth question: what about consciousness? I've suggested that consciousness might be a pattern of information on the boundary, but I've been deliberately vague because we genuinely don't know. The hard problem of consciousness, how subjective experience arises from physical processes, remains completely unsolved. We don't know why some physical systems are conscious and others aren't. We don't know what it feels like to be a bat, or an octopus, or a quantum computer. We don't know if consciousness is fundamental or emergent, physical or non-physical, computational or something else entirely. The holographic principle doesn't solve this. It reframes the question, but it doesn't answer it. If consciousness is a pattern of information, we still need to explain why some patterns are conscious and others aren't. We need to explain what makes a pattern feel like something from the inside. We need to explain the relationship between objective physical processes and subjective experience. Some physicists think consciousness is fundamental, that it's a basic feature of reality, like mass or charge. Others think consciousness is emergent, that it arises from complex information processing. Still others think consciousness is an illusion, that there's no real subjective experience, just physical processes that create the appearance of experience. We don't know which view is correct. We might never know. And here's what makes this especially difficult. Consciousness is the one thing we can't observe from the outside. You can observe someone else's brain activity, but you can't observe their subjective experience. You can't know what it feels like to be them. Consciousness is inherently private, inherently first person, And science is inherently public, inherently third person. There might be a fundamental mismatch between the nature of consciousness and the methods of science. Seventh question. Are we alone? If the universe is holographic, if consciousness is a pattern of information on the boundary, then other conscious beings would also be patterns on the same boundary. We would all be part of the same holographic structure. But where are they? Why haven't we detected any signs of extraterrestrial intelligence? Why does the universe seem so empty? This is the Fermi paradox, and it's deeply puzzling. The universe is vast. Billions of galaxies, each containing billions of stars, many with planets. The odds seem overwhelming that life should have arisen elsewhere. Intelligence should have evolved. Civilizations should have developed. Some of them should be far more advanced than us. They should be visible, detectable, obvious. But we see nothing. We hear nothing. We are alone, as far as we can tell. Maybe we're the first. Maybe intelligence is incredibly rare. Maybe civilizations destroy themselves before they become detectable. Maybe they're hiding. Maybe they're here, but we can't recognize them. Maybe the holographic structure of the universe makes communication between distant patterns impossible. We don't know. And this connects to a deeper question. What is the purpose of consciousness in a holographic universe? If we're patterns of information on a boundary, why do we exist? What function does consciousness serve? Is it just an accident, a byproduct of complex information processing? Or is it fundamental to how the universe works? Some physicists speculate that consciousness is how the universe observes itself, how quantum states collapse, how possibilities become actualities. In this view, consciousness is not a passive observer, but an active participant in creating reality. The universe needs consciousness to exist. Without observers, there would be no collapse of the wave function, no definite outcomes, no actual events, just a superposition of all possibilities. This is a radical idea, and most physicists are skeptical, but it's consistent with quantum mechanics. It's consistent with the holographic principle, and it would explain why consciousness exists, not as an accident, but as a necessary feature of reality. But we don't know if this is true. We don't know if consciousness plays a fundamental role in physics, or if it's just an emergent phenomenon with no special significance. We don't know if the universe needs observers, or if it would exist just fine without us. Eighth question. What lies beyond the cosmic horizon? The observable universe has a boundary, the cosmic horizon, beyond which light hasn't had time to reach us since the Big Bang. But the universe doesn't end at that boundary. There's more space beyond it, more galaxies, more stars, more structure. We just can't see it. If the holographic principle is true, then all the information about the observable universe is encoded on the cosmic horizon. But what about the regions beyond? Are they encoded on a larger boundary? Is there a hierarchy of boundaries, each encoding information about larger regions? Or is the cosmic horizon the only boundary that matters, and everything beyond it is somehow not real, not part of our universe? We don't know. The mathematics of holography works for bounded regions, but the universe as a whole might not be bounded. It might be infinite. And if it's infinite, then the holographic principle might not apply globally. It might only apply locally, to finite regions. The global structure of the universe might be something else entirely. And here's a possibility that's truly mind-bending. Maybe there are multiple cosmic horizons, multiple boundaries, multiple holographic descriptions of the same universe. Maybe the universe is like a hologram, viewed from different angles. Each perspective gives you a different two-dimensional projection, but they're all projections of the same three-dimensional object. Maybe our cosmic horizon is just one of many possible boundaries, and other observers in other parts of the universe have their own boundaries, their own holographic descriptions. If this is true, then the universe is not a single hologram, but a collection of overlapping holograms, each valid from a particular perspective. And the question becomes, which perspective is fundamental? Or are they all equally fundamental? Is there an objective reality underlying all these perspectives, or is reality itself perspective dependent? We don't know. and the mathematics doesn't tell us. The mathematics describes how to construct holographic descriptions, but it doesn't tell us which description is the right one, or if there even is a right one. Ninth question. Can we ever test this? I've talked about experiments, the holometer, gravitational waves, quantum computers, but all of these experiments test specific predictions of holography in limited contexts. None of them can definitively prove that our universe is holographic. The cosmic horizon is too far away. The Planck scale is too small. The energies required are too high. We might be in a situation where the holographic principle is true, but fundamentally untestable. The theory might be correct, but we might never be able to prove it. This is deeply frustrating for scientists. Science is supposed to be empirical, testable, falsifiable. But some questions might be beyond the reach of experiment. And this raises a philosophical question. If a theory is untestable, is it still science? Or does it become metaphysics, philosophy, speculation? Where is the line between physics and philosophy? The holographic principle straddles that line. It's based on rigorous mathematics, on proven results in quantum gravity, but its application to our universe might be untestable. Some physicists are comfortable with this. They argue that mathematical consistency and explanatory power are enough. If a theory explains many phenomena, if it unifies different areas of physics, if it's mathematically beautiful, then it's worth taking seriously even if we can't test it directly. Others are uncomfortable. They argue that without experimental verification, we're just doing mathematics, not physics. I don't know who's right, but I know this. The holographic principle has already changed how we think about space, time, information, and reality. Even if we never prove it's true for our universe, it's taught us something profound about what's possible, about the nature of physical law, about the relationship between information and geometry. 10th question, and this is the one that haunts me. What if we're asking the wrong questions? What if the holographic principle is pointing towards something deeper, something we don't have concepts for yet? What if space, time, information, consciousness, all of these are emergent phenomena arising from something more fundamental, something we can't even imagine? The history of physics is full of conceptual revolutions. Newton thought space and time were absolute. Einstein showed they're relative. Quantum mechanics showed that reality is probabilistic. The holographic principle shows that space is emergent. Each revolution required abandoning old concepts and developing new ones. Each time, we discovered that reality was stranger than we thought. Maybe we're on the verge of another revolution. Maybe the holographic principle is just the beginning. Maybe there's a deeper level of reality we haven't glimpsed yet, a level where our current concepts, space, time, information, even mathematics itself, break down and need to be replaced by something new. We don't know what that something might be. We don't have the language to describe it. We don't have the mathematics to formalize it. We're like people in the 19th century trying to imagine quantum mechanics. We lack the conceptual tools to even formulate the right questions. But here's what gives me hope. Every time we've encountered a conceptual barrier in physics, we've eventually broken through. It took decades, sometimes centuries. It required genius, creativity, persistence. But we broke through. We developed new concepts, new mathematics, new ways of thinking about reality. And we'll do it again. Somewhere, right now, a young physicist is thinking about these questions. Maybe they're reading this script. Maybe they're lying awake at night, wondering about the nature of the holographic boundary, or the emergence of time, or the relationship between consciousness and quantum mechanics. Maybe they'll have the insight that breaks through to the next level. That's how science works. Not through sudden revelations, but through generations of people building on each other's work, asking better questions, developing better tools, making incremental progress toward understanding. The holographic principle is one step in that journey. It won't be the last step. But let me bring this back to you. Back to the person watching this video, thinking these thoughts, experiencing this moment. You might be feeling overwhelmed. You might be feeling like reality has been pulled out from under you. You might be questioning everything you thought you knew about existence. That's the right response. That's what wonder feels like. That's what it feels like to encounter something genuinely strange, genuinely profound, genuinely beyond your everyday experience. But here's what I want you to remember. The strangeness doesn't make reality less real. The fact that you might be a hologram doesn't make your experiences less valid. The fact that space might be emergent doesn't make the ground beneath your feet less solid. The fact that time might be an illusion doesn't make this moment less precious. You are still you. Your thoughts are still your thoughts. Your experiences are still your experiences. The holographic principle doesn't change what it feels like to be you. It just changes your understanding of what you are at the deepest level. And that understanding is empowering. Because once you know that you're a pattern of information, you realize that patterns can change. You're not fixed. You're not determined. You're a dynamic, evolving structure, constantly processing information, constantly becoming something new. Every choice you make changes the pattern. Every experience you have adds information. Every thought you think modifies the structure. You are not a static object. You are a process, a flow, a becoming. And that process is you creating yourself, moment by moment, choice by choice, thought by thought. This is true whether or not the holographic principle is correct. This is true whether you're a pattern on a cosmic boundary or a collection of atoms in three-dimensional space. You are not a thing. You are a process, and processes can change. So what do you do with this knowledge? How do you live in a holographic universe? The same way you live in any universe, with curiosity, with compassion, with wonder. You ask questions. You seek understanding. You connect with other patterns, other people, other conscious beings, other expressions of the universe experiencing itself. You create, you explore, you grow. Because here's the final truth, the one that transcends all the mathematics and all the philosophy. You are here. You exist. You are conscious. You are experiencing this moment. And that is extraordinary. It doesn't matter if you're a hologram or a collection of atoms or a pattern of information on a distant boundary. What matters is that you are. What matters is that you can think, feel, wonder, love, create, understand. What matters is that you are the universe becoming aware of itself. And maybe that's the answer to all the questions we can't answer. Maybe the purpose of consciousness is not to solve the mysteries of existence, but to experience them. Maybe the universe doesn't need to be understood. It needs to be experienced. And you are how it experiences itself. You are the universe looking at itself through your eyes. You are the cosmos thinking about itself through your thoughts. You are reality experiencing itself through your consciousness. And every moment of that experience is precious, unique, irreplaceable. The holographic principle tells us that information is fundamental, that reality is stranger than we imagined, that the boundaries between things are not what they seem. But it also tells us something else, that we are all connected, that we are all patterns in the same cosmic structure, that the separation between you and me, between us and the universe, is an illusion created by the projection. At the deepest level, we are one. Not metaphorically, literally. We are all patterns of information on the same boundary, all projections from the same source, all expressions of the same underlying reality. When you look at another person, you are looking at yourself. When you harm another being, you are harming yourself. When you create beauty, you are beautifying the universe that is you. This is not mysticism. This is physics. This is what the mathematics tells us. This is the reality we live in. And knowing this changes everything. It changes how you see yourself. It changes how you see others. It changes how you see the world. You are not separate from the universe. You are the universe. And the universe is you. So live accordingly. Live with wonder. Live with curiosity. Live with compassion. Live with the recognition that every moment is a gift. Every experience is precious. Every consciousness is sacred. Because you are not just in the universe. You are the universe, experiencing itself, knowing itself, creating itself. You are a hologram, but you are a hologram that knows it's a hologram. And that knowledge is the most profound thing in existence. The cosmic horizon is 46 billion light-years away. The information that constitutes you is encoded on that distant boundary. But you are here, now, experiencing this moment. And that experience is real. That experience is you. That experience is the universe becoming conscious of itself. Welcome to the holographic universe. Welcome to the reality where everything is connected, where information is fundamental, where consciousness is the universe experiencing itself. Welcome to the truth that is stranger than fiction, deeper than philosophy, more beautiful than poetry. Welcome to existence. You are here, you are now, you are real. And you are a miracle.